In this class, I am going to discuss about the magnetic field produced due to a current carrying loop. Now, suppose this is a table. This is a table, and on its top, a single current carrying loop is placed in such a manner like this is a tabletop. This is a tabletop, and the loop is placed like this way. This one. This is a tabletop, and this, suppose this one, I can use a book. This is a surface, and the loop is like this. So if the loop is placed like this on the surface, then it produces the magnetic field, which definitely lies in the plane. If this is the loop, when current flows through it, it produces a magnetic field which definitely lies in the plane. This is actually, this loop is perpendicular to this blackboard actually, and the magnetic field lies in the plane of the blackboard. So suppose this single loop of radius a, and it's from its center at a distance x, a point P is considered. So definitely we have to consider a very small part AB of length dl, and it produces a very small magnitude of magnetic field dV at P, and that lies in the plane of the blackboard. This is the radius vector. Now according to Biot-Savart, BB is equal to mu naught upon 4 pi I dl sin alpha by r square. Now in this case, the loop's plane is perpendicular to the board, and the magnetic field lies in the board, because the current and the magnetic field produced by that current, these two always are mutually perpendicular. So this angle, the angle between board and loop's plane is 90 degree. So this angle is also 90 degree. So here alpha is 90 degree. So it turns to this. Now in this case, since this acts obliquely, so we can resolve this into two components. If we consider another element exactly diametrically opposite to AB, then this element also will produce this kind of magnetic field. So it can also be resolved into two components. This component, if this is theta, we assume if this is theta, then it is also theta, and this is dV cos theta, and this is dV sin theta. Here also this is dV cos and this is dV sin. So these dV, two components of cosine, will cancel each other, since they are exactly equal and opposite vectors acting through the same point, but all the sine theta components join together. So if we consider the total loop, all the dV sine theta components join together to produce the total effect of the magnetic field due to the complete loop. So to calculate the complete magnetic field, we have to integrate this. All the dV sine theta components. So mu naught upon 4 pi I by r square sine theta. All the constant components come outside and inside only there is dl. So considering the total loop, definitely that dl is the total circumference of the loop, that is 2 pi a. Now sine theta, in this triangle sine theta is a by r into 2 pi a, that is mu naught upon 4 pi 2 pi I a square by r cube. So now r is under root of a square plus x square. So this is the final result of the magnetic field produced by a single current carrying loop at a distance from its center. For if there are n number of turns, suppose in an armature we usually wound large number of turns to make the armature. That means there are multiple turns or multiple loops. So for n loops, just this expression is to be multiplied by n. Now there is a special option. If that point comes to the center of the loop, this point comes to the center of the loop, what will be the value of the magnetic field? Then this x turns 0. So here x turns to 0 and these two 2's cancelled out. So a cube, and with a cube a will be also cancelled out to produce a square below as denominator.